This is the second video about linear systems of differential equations that you should be watching as you start to study Chapter 3. This was the beginning slide that I had on the first video about linear systems. And linear systems are kind of fun. Well, at least I think they're kind of fun. You can end up finding these things called eigenvalues and eigenvectors and use the eigenvalues and the eigenvectors to find the general solution and also to understand why the phase plane looks the way it does. Now, I got so excited about talking about eigenvalues and eigenvectors, or I'm so excited today that it rubbed off on my son. We have a guest viewer in the classroom today. Over off here to the right. There's my son, Tyler. He's 9 years old right now, and who knows, maybe in about 10 years, he'll be taking differential equations and he'll watch this video and see himself. He was so excited about eigenvalues and eigenvectors that he just couldn't resist coming. So hopefully that excitement will rub off on you too. Actually, with that previous lecture, my youngest daughter Bethany was actually in the audience, but I didn't put the camera on her. Maybe we'll have to have her come back and view another lecture also. So this was the situation. We had this system, this linear system. What makes it linear? Well, first powers of x and y. We also want to say, at least when we're in Chapter 3, that linear systems don't have any constant terms. So you don't see any constant terms over there. And it's important to have a vector perspective and also bring in the idea of a matrix. The vector perspective is important in terms of really understanding how the vector field is related to the solution curves. And the matrix perspective allows us to focus on the coefficients of the x's and y's. And in fact, those coefficients completely determine what's going to happen. They completely determine what the general solution is going to look like and what the phase plane is going to look like. I also showed you, as usual, that the first thing you want to do is find any equilibria, setting the right-hand sides equal to 0 and solving for x and y. And with linear systems, there's this fundamental fact that a matrix A times y is going to equal the 0 vector. That equation is going to have 0 as a unique solution for y. That's called the trivial solution, if and only if the determinant of that matrix is non-zero. And a corresponding important fact for differential equations is that the corresponding differential equation that looks like that, dy dt equals a times y, has 0 as its only equilibrium point, if and only if, once again, the determinant of the matrix, the coefficient matrix, is non-zero. So that was one thing that we looked at. We also looked at the idea behind eigenvalues and eigenvectors. I just love those words too. It just sounds so neat. Eigenvalues and eigenvectors. It's kind of a mixture of German and Anglo-Saxon. Eigen, I think in German, means characteristic, and then values, of course, means numbers. What do we seek? We seek non-zero vectors, v, so that a times v is lambda times v, where lambda is a scalar. Lambda is a scalar. In other words, a number. And the important thing about this was that it's going to help us find straight line solutions. It's motivated by looking at the vector field and seeing that the vector field quite often for linear systems, not always, but quite often, seems to have lines of vectors that point directly away from the origin or directly toward the origin. Well, we want to find v and lambda because ultimately functions like this, e to the lambda t times an eigenvector, where lambda is the corresponding eigenvalue, are going to be solutions, and we're going to check that today in this video. How do we get there? How do we find lambda and v? Well, we take this equation, subtract lambda v from both sides to get this equation right here. Think of v as being I times v, where I was, in this case, a 2 by 2 identity matrix. You multiply it times any vector, you get the vector back. That allows you to see that you can factor out the common factor of v to get this equation. And then we use that fact from the previous transparency to give a condition when we're going to have non-zero solutions for v, because we do want non-zero solutions. This is a homogeneous algebraic equation. We're looking for non-zero solutions for v. It had only the trivial solution if and only if the determinant of this matrix is non-zero. So it's going to have non-trivial solutions if and only if the determinant of this matrix is 0. So we need to set that determinant equal to 0 and solve the resulting equation for the unknown lambda. Let's do that now with the particular system that we have. So the coefficient matrix A is -2, -2, -2, +1. We need to find A minus lambda I. That matrix minus lambda times the identity matrix, which means we just multiply each entry of the identity matrix times lambda. Lambda times 1 is lambda, lambda times 0 is 0. So we get this matrix. We need to do the subtraction now. And you just subtract entry by entry. We have a -2 minus lambda up in the upper left-hand corner, -2 minus 0 in the upper right-hand corner, -2 minus 0 also in the lower left-hand corner, and 1 minus lambda in the lower right-hand corner. We need to take the determinant of this matrix. What's the determinant? Remember from the last video or from reading your book, you should see that you need to take the product of the entries on the main diagonal and subtract the product of the entries on the off diagonal for a 2 by 2 matrix. Just leave the lambda in there as an unknown. There's the product of the entries on the main diagonal, and subtract the product of the entries on the off diagonal. You do need to be careful not to make mistakes with minus signs, so you need to be extra careful about putting parentheses where they belong and double check to make sure you don't make a mistake. I will have to be careful also. Let's see, for this part I'm going to FOIL it out. I've got -2 times 1 is -2. -2 times minus lambda is +2 lambda. Negative lambda times 1 is minus lambda, and then a negative lambda times negative lambda is plus lambda squared. Don't forget about this part. We've got 3 minuses, still giving us a -4. So what we get is a quadratic equation in the unknown lambda. There it is. We want to find values for lambda that make this equal to 0. We want to set this equal to 0 and solve for lambda. We could use the quadratic formula, but I've chosen the numbers so that it's easily factorable as lambda plus 3 times lambda minus 2. Meaning our 2 eigenvalues are going to be -3. I'll call that the first eigenvalue, and I'll label it lambda sub 1. And +2, which I'll label lambda sub 2. Those are the 2 eigenvalues. For any 2 by 2 matrix, you're either going to get 2 real distinct eigenvalues, or you might get 1 real eigenvalue that's really what's called a repeated root. For example, if you can factor this polynomial as the square of, say, lambda minus 3. Lambda minus 3 quantity squared. Lambda equaling 3 would be the only eigenvalue in that case, but we'd call it a repeated root eigenvalue because lambda minus 3 would occur twice in the factorization of this polynomial. This polynomial has a name. It's called the characteristic polynomial of the matrix. Or you could get complex number solutions, and we'll see in another video, and when you get to section, I think it's 3.4, you'll see what to do when you get complex number eigenvalues. But from this point on, with real eigenvalues, we need to find eigenvectors that correspond to each of these eigenvalues. And they're going to end up being not parallel to each other. They'll end up being what's called linearly independent, which ends up being very important as far as finding the general solution. How do we find those eigenvectors? Well, let's focus on the eigenvalues one at a time. Start with lambda 1 equals negative 3. Go back to that original eigenvalue-eigenvector equation that I had. This one. And plug in lambda equals negative 3. And solve the resulting equation for v. We could think of it in matrix form if we like. But it's probably better to think of it in terms of two scalar equations. Thinking of the unknown vector v as having components x and y, and thinking about the corresponding scalar equations you would get, we get negative 2x minus 2y and negative 2x plus y for the left-hand sides of the equations, because those were the right-hand sides of the original differential equation. And on the right-hand side of these algebraic equations, I need negative 3 times v. Separate those into components. I have negative 3x on the right-hand side for the first one, and negative 3y for the right-hand side of the second one. I'm just multiplying this arbitrary vector by negative 3. Solve this system of equations. And if you've done it right, you should get non-trivial solutions. These equations really end up being redundant in the following way. Let's add 3x to both sides of the first equation to get it to look like this. And let's add 3y to both sides of the second equation to get it to look like this. And if you look at those two equations, they really mean the same thing. They're equivalent. They have the same solution set. The second equation is negative 2 times the first equation. So they're redundant. You really only need one of these equations. Let's take the first one and use that to find your eigenvectors. How does this help? Well, all you need to do now is just pick some non-zero number for y. Pick something simple like 1. And then use this equation to find out what x would have to equal. If y is 1, x is going to have to equal 2. The vector v, whose first component is 2 and whose second component is 1, will be an eigenvector corresponding to the eigenvalue negative 3. Now that's not the only eigenvector. Any non-zero scalar multiple of this will also be an eigenvector for the eigenvalue negative 3. There's an entire line of eigenvectors. All non-zero multiples of this would work too. So your answer, actually for the general solution, will not end up being unique. There are different ways of writing the general solution. Anytime you solve an initial value problem, you in the end will get the same function for the solution of the initial value problem. That follows by the uniqueness theorem. But as far as how you actually write the general solution, it turns out there are lots of equivalent ways of doing it. Don't multiply by 0 though. By convention, 0 is never an eigenvector for any eigenvalue. Now go to the other eigenvalue. That was 2. And think about the same equation with lambda replaced by 2 instead of negative 3. Think of it in terms of scalars. I've got negative 2x minus 2y and negative 2x plus y on the left-hand sides again. And then 2 times x and 2 times y for the right-hand sides. Get 0 on the right by first subtracting 2x from both sides of the first equation to get negative 4x minus 2y equals 0. And then for the second equation, subtract 2y from both sides to get negative 2x minus y equals 0. And those equations are equivalent. Multiply this second equation by 2 and you'll get the first equation, for example. So they're redundant. I can just think about one of them. I'll think about the second one. I'll solve it for y in terms of x. And I get y is negative 2x. So that means that I can pick x to be something non-zero, for example, 1, and then y is determined by this equation to be negative 2. So I'm going to label that v2. That's the second eigenvector, which corresponds to the second eigenvalue, lambda 2 equals 2. Maybe I'll label this one v1. That corresponded to the first eigenvalue. We're almost done. We've almost got the general solution. In fact, that seems to work best here. In fact, the general solution, when you've got linearly independent eigenvectors like these are, these two vectors are not scalar multiples of each other. They don't point in the same or opposite direction. They're not parallel. When that happens in the 2 by 2 case, this is going to be the form of your general solution. An arbitrary constant times e to the lambda 1 t, where lambda 1 is the first eigenvalue, and v, multiply that times the vector v1, where v1 is an eigenvector corresponding to the eigenvalue lambda 1, and then add another arbitrary constant times e to the lambda 2t times v2. So for this problem, lambda 1 is negative 3, so I get negative 3t. v1 is the vector 2, 1, or any non-zero scalar multiple of that. And the second eigenvalue is 2. And v2 was 1, negative 2. This vector-valued function, which will describe a parametric curve if you have particular values for C1 and C2, is your general solution. We can use this, as usual, to solve any initial value problem that we want, although compared to Chapter 1, it gets a little bit more painful. What will initial value problems look like? Well, you might have, say, y of 0 equals the vector 4, negative 3, or something like that. And you'd need to substitute t equals 0 in both spots there and set the resulting equation equal to 4, negative 3. And you're going to get two scalar equations in the two unknowns, C1 and C2. So you'll have to solve the resulting linear system for the unknowns C1 and C2. T equals 0, e to the 0 is going to be 1, so I guess in this case the resulting equations would look like this. All I did there was I substituted in t equals 0 here and here. E to the 0 is 1, so this becomes 1 and this becomes 1. And then take the resulting vector equation, set it equal to 4, negative 3, and write it as two scalar equations. Just solve that system either by elimination or substitution. Getting close to ending this, we're going to have more videos about linear systems, trying to relate this to the phase plane, for example, and to the kind of equilibrium point that occurs at the origin. Turns out that, for example, if you have an initial condition that is parallel to, say, this vector, then C1 will end up being 0 for that initial value problem, and your solution will look like this. And based on the fact that e to the 2t grows to infinity as t goes to infinity, the resulting solution curve would go away from the origin as t increases. On the other hand, if you end up picking an initial condition parallel to this vector, if you put its base at the origin, then C2 will end up being 0 for that initial value problem, and you'll get a solution that looks like that, which will go towards 0 as t increases because you have e to the negative 3t. So those will correspond to solution curves that go straight toward the origin as t increases. The origin will end up being what's called a saddle. It's not a sink, not a source. It's actually not a node, although I suppose it's most similar to a node. Solutions will go directly toward the origin from certain directions, directly away from the origin, from other directions, and actually most other solution curves in the end will end up going away from the origin close to this eigenvector here, because this term will get very small as t gets large. I'll end today's video by showing you a few things on Mathematica related to matrices and vectors. Matrices in Mathematica are really certain kinds of lists. Though if you've got the basic math input palette, that should look better. If you've got the basic math input palette, like I do over on the right here, you'll notice there's a 2 by 2 matrix button close to the middle. And you can enter your numbers as you see them and as you see them in math books. And for this example that we just did, -2, -2, -2, +1, and I'm tabbing over from each square to get to the next square. I'll enter that, and you'll notice it's comes back with output that looks like a list of lists, a list of points, although in this case you actually wouldn't want to think of these as points. You want to think of that as being the first row, and this as being the second row of the matrix. Here's something very nice. Mathematica has built-in commands for eigenvalues and eigenvectors. So there we see our eigenvalues, -3 and 2. And the corresponding eigenvectors would be given in the same order. They would correspond to the eigenvalues above in the same order. 2, 1 is the first eigenvector corresponding to the eigenvalue -3. -1, 2 is the second eigenvector corresponding to the eigenvalue 2. This is different than the one I had. The one I had was +1, -2. But they're parallel. Points in the opposite direction. Mathematica chose the x to be -1, and then y was -2 times x. The y was +2. You can check that if you multiply the matrix A times one of these vectors, you'll get the scalar multiple of that vector. Matrix times a vector on Mathematica, you have to actually not do a times symbol, you do a period, a dot. Capital A dot V will multiply the matrix A times the vector V. Oops, I need to plug in what V is. I'll replace V with 2, 1. That's the first eigenvector. So think about what we should get here. AV equals lambda V. Lambda was -3 here. We should get -6, -3. And we do. AV equals lambda times V. -3 times V is -6, -3. And with the other eigenvector, -1, -2, the eigenvalue was 2, so we should get -2, 4. And we do. If you pick some other vector that's not parallel to one of these, for example, the vector 1, 1, you won't get a scalar multiple out. That vector that results is not a scalar multiple of V, of 1, 1. Because it's not an eigenvector. You pick some other vector in the plane besides on those two lines, and you won't get the result that it's a scalar multiple of that vector. And that's a way to test whether or not your math is right. You go back to those eigenvector equations that we solved to get the eigenvectors. If you don't get redundant equations up here, you know you've done something wrong. So go back and check your eigenvalues. Well, let's see, we're heading up on 30 minutes here. I think we'll end it right there.